So, let us see now, this is the fifth lecture, that means last lecture of systems approach, and again we will be studying lot of statistics, be it for probability estimation or be it for learning or training session in AI/ML. Okay. So, let us say there are certain characteristics, they are very important for our data, and mostly we will focus on estimation of which is an important parameter. So, how we will determine that the data we have it is in line with or it is we can name it or associate it with the distribution. Okay. We want to give one statement, my data follows this distribution, and that solves a bigger problem. So, in this lecture we will see what are the methodologies that are available for associating our data with a distribution, because then only the job becomes easier for us to model other events which are applicable to a domain. So, we call first is determining the, so first let us see the approximate approaches, one of which is nature of data. Let us say I am trying to assess, I am having a data with me where I am measuring shaft diameter produced in manufacturing. By common sense we can tell it will follow a normal distribution, either it will be 0.1, 0.2, 0.3 mm less or 0.1, 0.2, 0.3 mm more. So, it is the nature of data that we have, that is one way of it, and then other one is probability plot. I mean giving or considering a data by distribution, but verifying it on probability plot gives further confidence to us. And then we have statistical estimators like viable distribution, maximum likelihood estimator, and then Bayesian estimator will be studying, not as part of assessment, but combining data from two sources. We will be solving different problems, and last is common cause failure, if we have rather some point to be made in this lecture. So, as I mentioned, the applicable criteria. So, we know that we have two types of data, discrete data and continuous data, and continuous data will require normal, exponential and viable distribution, log normal distribution, and discrete data will have Poisson, binomial distribution and all. So, to that extent we can classify, determine the applicable distribution, which category we should go for. But the question is, given a data set, how to select most appropriate distribution. Okay? This is a question, because these models are used for prediction of reliability and safety, very important parameter, and we want that uncertainty should be to the extent possible to the minimal level. Okay? So, as a choice of distribution should represent the data itself. This is the key feature. So, whether it is a regression analysis, we will discuss that also, not in this lecture, sometime when we talk about AI/ML, or we have this probability plotting, or we have some estimator. So, let us see how much we can cover in this lecture. So, let us see determine applicable distribution, nature of data. If we say based on the nature of data, we are giving certain, the normal distribution is used on a production line involved in manufacturing of shafts, the variation of diameter and length, and shaft is characterized using normal distribution. So, there it is very convenient. So, generally for manufacturing normal distribution, this is just one example, it fits well. But suppose if we are doing live test data, if we are doing, then viable distribution as such people use it because it gives information about other distribution also. So, but generally in research, in fact, Weibull analysis has developed as a field. This distribution has so much of potential, not only in life prediction, but in many other prediction approaches also, where we want to give shape to data that we have tested, and we want to derive some information like characteristic life, or even trying to see whether it is saving, whether it is other distribution can better represent our data. So, another log normal distribution. This distribution allows some sort of independence in the data, and as we said, if the log of that parameter is a normal distribution, then we say that parameter we call it a log normal distribution is following. So, log normal distribution, I think in PSA, log normal or probabilistic risk assessment, log normal distribution gives us the edge when we want to characterize my component failure probability, not only component failure probability, but uncertainty associated with that as a error factor. So, it becomes very convenient as a one parameter error factor. We are associating uncertainty with the data, and during Monte Carlo simulation, these two taken together for all the components in the at the input of the fault tree, we take the result to the top, and we get final estimate of system failure probability. At the same time, we get uncertainty associated with that. So, log normal distribution is a sort of a key to having its use in probabilistic risk assessment. Then binomial distribution. Binomial distribution is used when we have a different combination. You know that redundancy is part and parcel of any safety critical system. So, if I want to assess, I have got three component, a redundant component, and my target is to achieve 10⁻³ as the failure probability. If two components fail, what happen? If one component fail, what happen? So, if I want to get the probabilistic feel about that, I can do in this. Let us say I have provided redundant devices. I have provided 7 redundant devices to shut down a system. Now, and they are all identical. How many devices will be sufficient? So, if my target is to achieve 10⁻⁷, then let us say 7 out of 3, if the probability is target is 10⁻⁵, and if I get that value, then binomial distribution is very useful. And regarding Poisson distribution, we have talked about it. It gives the spread of statistics in the either physical length domain per feet or in time domain. Okay. So, it is very important parameter, because finally a decision has to be taken. However, it may be used that even though these heuristics serve a good purpose, when the scope of the problem is rather wide, the available resource and the input information prohibits a detailed data analysis to determine applicable distribution. So, once we, on the basis of nature of data we have taken, the next stage should be that we take, let us say I have gone for a exponential distribution. Now, what I will do is I will plot this data on the exponential probability paper. These papers are available in open domain. You take the paper and plot. If there is a straight line, or the scatter of the data across a line will tell us whether is this distribution, and later on we can do a coefficient of correlation. See, we have data here scattered all across. When we put a line, this side also, that side also, so in between we draw a line. So, if we do the regression analysis, and I give you one example. So, if that tells that the spread is coming, that coefficient of correlation R is coming more than 0.9, then I will say that this particular data line is representing this data very well. If it is 0.7, 0.5 and all, then we will say it will. So, first we got from for nature of the data, then we came to the probability paper, and then again if we had a doubt, we did the regression analysis. So we came, okay, now my data is following or not following a exponential distribution. Okay. So approximate approach is good, but finally we have to fine tune, at least we have to do sampling of for many data, so that we are sure that we are using the correct probability model for our analysis. One limitation of this method is that visual judgment of how well the data is drawn. We might say that yeah, it is okay, the data is fitting into the line, but then we require a regression analysis. Coefficient of correlation should be 0.9 as I mentioned, and then it will confirm that thing. Then I think chi-square methods are also there. Chi-square methods also can tell if the chi-square is around 17, it gives us a confidence. So chi-square method I will cover in the next lecture, and of course the regression also we will discuss as and when it is required, so that we are pretty sure that we are having data, and we are pretty confident of representing our data, because that builds, that is a very important quality characteristic of modeling of PRA. Even though Weibull distribution we saw earlier, Weibull distribution has become one of the analysis choice, and this beta is equal to see, if we plot a line on the Weibull plot, let us say if my data are there, and if the scattered is there something like data point something, and we put a line. Okay. Now we saw in previous regression analysis, but if I want to do a simple analysis, I plot there whatever data it is, I plot that data on this graph, and then I will see what is the slope of the line. Okay. If the slope of line is 1, then and how it is that tan theta is equal to perpendicular upon base. So we get that distribution. So we get, if that is 1, then it is exponential distribution. Yeah, as I mentioned here, beta is equal to 1. If it is 3 and 4, it is a normal distribution, and there are many more indicators if we get an insight into the data. So Weibull distribution is analysis is one of the best way and very popular tool for analyzing the data and trying to assess its distribution. So other than modeling lifetime parameter, it can be used as a way of having not approximation, but exactly knowing the distribution. And even if I plot it here, the data, and if I get I can do always a regression analysis here. So doubly sure about my data that it is fitting, the line which I have considered is fitting the data, and it represents my data points. Okay. Now let us talk about estimation. We do estimation as such also, but what is the best way? Like normally it can be visualized like this. Whatever parameter we estimate, it is a estimator of that particular parameter. Let us say I am talking about mean. I have done, and I have 10 quantities I have added up and divided by 10. Now whatever answer I got, let us say x. So x will be called as estimator of mu in real sense. So how to get the maximum likelihood estimator? Okay, this is the problem, and that you will see with a simple example of exponential distribution what we are talking about here. So maximum likelihood estimation is one of the most commonly used point estimation procedure from the PDF of a given random variable. Consider a test where there are n independent sources are there, trials were carried out, and the outcome was, if x is the random variable, the outcome was x is x1, x2, x3 and xn. Okay. Now this information can be characterized by PDF, probability density function of x and theta. So what is theta is my parameter I am trying to work out, where theta is the parameter of the distribution. So this is very important step. So what is the likelihood that we are talking about theta, and these are the observation, and so you know that different observation, joint probability distribution you would have heard of two parameters is nothing but multiplication of I is equal to 1 to n and PDF of x a in theta. So it is multiplied. Okay. So that means likelihood is nothing but if I have a exponential distribution e raised to power minus lambda into e raised to power minus lambda t, it will be giving a product. That means exponential term will be added over here. So, so that is how we get the likelihood function. Now, maximum likelihood function requires determination of the theta cap. What we talk about the from x we are deriving theta, but we want theta cap in the sense that we want the estimator for theta. This is the so likelihood of likelihood of x represented by theta cap is having more likelihood than likelihood of xi into theta. Probably and once we do that, we are pretty confident that my likelihood estimator has given me this result, and this is correctly representing my data. Till then, if you don't have likelihood estimator, you will say for mean add quantities divide by 10, and that you will call as a estimator. Now, if why we are saying it is a estimator, because if the new values are added to the x for 10 we had, let us say if we go x 11, 12, 13, 14, definitely the parameter will change. So this parameter, likelihood parameter, gives us the real scenario actually, you know. So the for maximizing the function, the gradient should be 0, you know that del upon del q, it should be 0. This is the condition for maximizing of this function. So let us do, if we do maximization, so we first what we do is the gradient will be 0 when we reach maximum. This is a common rule. So we have a second derivative, first derivative. So del upon del theta, and we take log of this, okay, and then this is equal to 0. So if it is equal to 0, then only we will call that maxima has reached or minima has, but here in this case it is a maxima, because gradient of differential is 0. Now let us understand and get this idea by going through one problem of exponential distribution, and then we'll get it what we are trying to say. Suppose we have test and there are n observation, T1, T2, T3 up to Tn. The parameter to be estimated is failure rate. Okay, so this is equivalent to our theta, what we showed there. Find the maximum likelihood estimator for lambda. Okay, so up to here it is clear. Our quantity of interest is lambda. Now here likelihood of given Ti, T1, T2, T3, and for lambda. So it is like, you know, two parameter joint probability function. So we can represent it by multiplication of I from raised to 1 lambda into exponential minus lambda t. And further if we do calculation, so likelihood function will come as Ti lambda is equal to lambda n, okay, because we have done the integrate this thing multiplication, and exponential minus, because this term will get added, e raised to power minus lambda, they will get added up, and Ti remains same. Now if I take the natural log of this, len L is equal to n log. So log means n lambda len L minus lambda into this one. So probably we have this point natural log, then we have len L is equal to n len lambda minus lambda. So this term will come over here, okay. Exponential term will go away here, and differentiating both the sides. Now del len L upon del lambda with respect to lambda. we get n upon lambda and this thing. Now if I reorganize everything, my lambda estimator is equal to n upon summation of time is equal to 1. Okay. Now to check this estimator, you go for second derivative. So whether it is a maximum or not, if we go for second derivative, so d2 delta 2 L upon delta lambda 2 is equal to, and this is less than 0. So that means we have reached at the maximum point when we did the first derivative we took, and lambda cap, that is likelihood estimator of lambda is equal to n upon the lambda. Now if I want to take the so this 10 component, n was 10, so many tests were there, and then we can get a, like, it is very simple that it is the failure rate value we are giving for summation of the time, n divided by all summation of the time, that will give us failure rate per hour if the time unit was used per hour. So this is called maximum. It is very useful for exponential distribution. We could solve this because exponential distribution is very simple and elegant. We can do it for other distribution also, but it becomes complicated. So we have demonstrated the maximum likelihood estimator, its significance, and its why it is called likelihood that way. So we can model the same thing correctly in our PRA model. One more Bayesian estimator is there. Why its importance is there? Bayesian estimation means many times we come across a situation that in our plant we have collected some data, but that data is not sufficient. So what to do? We are getting large uncertainty because of that, and I am giving a very simplistic view of the situation. So what I do? So I got one option. I see the same parameters value, let's say failure rate. I'll see in the generic source. So can I use that thing? Yes. Bayesian estimation allows integration of the values that are available in generic source, which are called as priori value. That means we have this information available, and then from my plant data, let's say I had some pump. Now it's a failure rate. I have got some 1 year experience, which is not sufficient. But in generic database, similar component matching the qualification, we have the data available. So the assumption is I don't mind taking data from generic sources and trying to enrich my estimator. So that is where my plant specific data is represented are failures in t time. So I'll get one more failure estimation, and here we have PDF of this thing. Now I do Bayesian updating. Bayesian updating, when I do, I get a posteriori value. That means a final value which I got because of combining priori and likelihood estimator. Now the question is, as your plant experience goes on increasing, you will find that this priori value is coming very close to the likelihood that our plant specific experience here actually, So this is the beauty of this posteriori or Bayesian updating that we have in statistics. Okay. So how it goes on? See, we know the conditional probability, or we know joint probability density function. Okay. So let G lambda is the joint probability density distribution of lambda. Okay. If Ft lambda is the conditional probability of, because T depends on lambda. So if is the conditional probability of random variable T given lambda, okay, then T dash lambda is the joint probability of random variable, okay, joint probability of random variable, and the joint probabilities are given by multiplication, 1 into n Ft given lambda. Now how this can make a Bayesian estimator. Now Ft is the marginal density function of the random variable T, and if lambda T is a joint posteriori probability, f lambda t is the posteriori probability, then our Bayesian updating formulation by rearranging the value will get like this. You may be knowing that even in the thing marginal density function, we have let us say probability of A into B is equal to probability of A and probability of B given A. Okay. Now, this same thing can be also be written as probability of B into probability of A given B. Now, this term and these two terms can be equated, and let us say if we want probability of B is equal to probability of B is equal to probability of A into probability of B given A, B given S, sorry, and then probability of B if we want, then probability of A given B. So, similar thing we are doing, and this is called Bayesian updating actually. So, this exercise we can do, and if it is whether you consider the joint probability density function or any. So, we are trying to talk here in terms of joint probability density function, and this is how we can we can create a model, and Bayesian updating can be done. It is a very useful method in probabilistic risk assessment, because always the plant specific values are not the way you have it. You have less data, especially if the plant has started operating it. As I mentioned you, data comes only slowly. So, use the generic data. You had already you created a model, but now you have Bayesian updating. Go on updating that data in maybe 10 years or 15 years time. You will have your own distribution actually, because your model will approach to plant specific data. So, this is what the advantage of Bayesian updating, and it is very significant. It is very extensively used in probabilistic risk assessment. Okay. Well, in this week we have discussed which are directly relevant to PHM, and we have seen statistics probability fundamental that support PRA, and also part of AI/ML language, AI/ML in the sense of training, learning and feature extraction. Special attributes like safety and security, quality, etc. also we have considered. Now, there is a book I think written by me and Professor Pett, Risk Based Engineering Chapter 8. We can refer this as a reference for these models and methods, and of course, this doesn't apply because week 4 we are going to now discuss sensors and degradation. So, in week 4 we will discuss the degradation of the material, degradation, sensors and DAQ, data analysis system, okay, and how it works as part of PHM. Thank you.